Testing. You're going to be on Google Classroom today, so if you're not there already. Try to get there now. There's going to be, if it's not already posted, it should be popping up here in a second. A couple things you'll need. One is a Google Doc file. A Google Doc. You'll be filling some things in on today. The other is a Google Slides file that you'll likely have to take along and work on as you leave. There might be some time toward the end of our time together today where you can start to dig into that. We're going to show you kind of to get started with that. But we probably won't get through all of it. We're going to leave some of that for you to do. It makes it a little bit more creative, and it gets you looking at it a little bit more personally rather than just listening to us talk about stuff from our perspective. It lets you go out and dig up something that helps you understand it from your perspective, which makes a lot more sense, we think. So classification, vocabulary we'll go through together. It's kind of definition stuff that is mostly review. That's kind of what I want to hit together so that you've heard one standard description, one kind of this year perspective on this stuff, because it's almost certainly terms you've heard prior and that you can probably fill in from your memory up to this point. And we want to make sure that whatever you have in your definition, your personal own words definition, it not only matches what we have, but includes everything that we want you to include. So you can probably define a lot of the terms that you'll see on that doc file, but maybe you wouldn't have all the details that we're going to give you today. So try to keep up with that. We've found in the past that when we give notes in this way, that a lot of times we'll have students go, hold on, wait a second, can you go back, and that kind of stuff. And we may or may not do that today. The reason being, we want you to be going to look. If you need to see something again, we need you to go make the habit of going back and looking at the doc that will link with the video stream, and you go back and look at it again if you need to. Because part of what we want you to get used to doing in here is utilizing the resources that you have. And as the year goes on, it gets you more and more like what a college lecture class of this type would feel like. So that you know that, in the case of a lecture chemistry course or something at college level, that you wouldn't have the opportunity to ask the professor to go back because they just plow ahead so often in a class like that. So, we will post the link. This is the first day we're recording this stream. Last week with the demonstrations, we had so much going on small up close that doesn't record well from the top. We will have a link in there for the video that we recorded like 2 years ago with all those demonstrations sort of up close so you can see them rather than seeing them from a great distance. So this is the first week that'll be linked as a stream video link, and we'll post that in Google Classroom for a large group so you can find it there and try to keep it near the top so it's always available to you in this class or something. In case you're not in Google Classroom, I think when I checked the other day there were still 4 or 5 people who weren't. So there's the code if you still need to get in to get into Google Classroom and be able to access the files we're talking about. Makes it a lot easier for that. So you don't need to draw this out, but this is kind of the roadmap we're heading toward. One thing we're going to cut out of it this year is we're not going to go down on the right side, those green boxes, we're not going to go down as far as the terms homogeneous and heterogeneous mixtures. It's kind of a cumbersome couple of words. It's something that is sort of talked about without using those words in different ways. And we've sort of, as a team, decided that we don't need to get into those details as much anymore. But we will talk about how materials can be classified as substances or mixtures, what makes those things different, and then what makes elements and compounds different, and then some variety of information about homogeneous mixtures, because that's a really big topic. Homogeneous mixtures can go a lot of different directions. So as far as the terms that we try to pretty much put them in order, they pretty much follow the sequence of things according to the slides. So if you keep it up okay, the order should pretty much just follow. Substances are a material that has definite composition. Materials can be solids, liquids, and gases, or a blend of those states potentially, but it's something with definite composition. Definite kind of means like has a very particular definition in this case. Definite, something with a very firm definition, and that's the only way you can describe it. In other words, it means the same thing no matter where. Right? Like the word, I don't know, horse. The word horse is a horse. Horse is a horse, of course. Everywhere we go. And it means the same thing. It doesn't mean like horse doesn't mean one thing here and then something else in Canada, for example. Or one thing here and something else at the Century High School. Force is force. Well, a compound, an element, those are substances. They mean the same thing no matter what. So here you see gold bar. Gold is gold no matter where you go. On the bottom, I think sugar. Sugar's sugar pretty much wherever you go. Well, there's different kinds of sugar, but they're all compounds, so they're all substances. Doesn't mean a different thing no matter where you might be. Elements are a substance. So under substances, then, we have elements and compounds in that earlier flow chart. Elements have one kind of atom only. And we've talked about this periodic table a bit here and there on things maybe casually. We're going to be getting a lot more into the periodic table. Students come in. One of the first questions I get first day of school every year is, who's memorized the periodic table? And I don't know. I tell my students no. So that's kind of a silly drill, waste of time. But you're going to find out that as you do the homework and practice throughout the year, you're going to memorize a lot of it without doing it on purpose. Elements on the periodic table, 118 of them that we know of so far, are defined by the number of protons they have. One kind of atom. In that gold bar, all the atoms are the same in terms of the number of protons that they have. Gold atoms have 79 protons. Sulfur has 16. Helium has 2. Anywhere you go, that's true. That's the definition of a gold or sulfur or helium atom. It's defined by its protons. And they might say, wait a second, what about electrons? What about neutrons? Those things are important too, but they don't define it. Protons are like the DNA of the element, just like your DNA is you. You can cut your hair off tonight. You can dye your hair. You're going to look very different from the outside, but your DNA makes you who you are. The hair that grows back is determined by what your DNA says. The protons define the atom just like your DNA kind of defines your biological reality as far as what you look at us. You won't have to worry about drawing pictures per se like so, but you can kind of see what we call a planetary model, or a way of sort of drawing out an atom with protons and neutrons and electrons in it. You might have seen pictures like that in the past. Sulfur is defined and helium is defined in the same kinds of ways, no matter where you go. Now, an important description or delineation on the periodic table is that staircase line. On any periodic table, we can usually see it printed in, and many periodic tables we can at least kind of figure out where it would go. Put an easy staircase that separates the next kind of two words we want to make sure we understand the differences in. We've got metals and non-metals. So our periodic table, just to remind you about this, again, you've heard this somewhere before, at least once. Everything to the left of that staircase line tends to be classified as a metal. Everything to the right of it tends to be classified as a non-metal. The only real exception is hydrogen. The hydrogen is kind of way up there in the top left corner. And that one's really kind of a non-metal that likes to act like a metal sometimes. More or less, that staircase is an important differentiation because the elements can be classified in that big, easy grouping first. And those elements can be used in different ways, whether they're metals or non-metals, because of the properties and the ways that they bond. Compounds. The other kind of substances. Again, a very definite description, a very definite makeup that doesn't change from place to place. Compounds contain at least two kinds of elements, sometimes many more than that. Compounds have at least two kinds of elements, at least two kinds of atoms then, in a fixed whole number ratio. That's in red and it's underlined in bold. Whole number ratio. We do this our whole life. H2O is a ratio 2 to 1. Sugar, C6H12O6. Glucose, that's a 6 to 12 to 6. Or if you simplify it, it's a 1 to 2 to 1 ratio. That ratio is the definition of glucose at atomic molecular level. So those whole number ratios. Sodium chloride, here's a bigger sugar molecule. Something like a copper nitrate, which is a really cool blue crystal. I think you'll see here in a second. Even if it has parentheses like that, you've certainly seen compounds written that way before. Even if it has parentheses like that, it has a very particular ratio to 1 copper, 2 nitrogens, 6 oxygens, copper, 2 nitrate. That's what we call that. Would always have that ratio. If it doesn't, it's not copper, 2 nitrate.
These formulas are important too. I had somebody this morning that's in their AP Chem that didn't have regular Chem that was concerned with when you see the formula of copper nitrate down there, when you see that NO3, which is referred to as nitrate, we're going to learn that moving forward, which is also known as a polyatomic ion. And the 2 outside of that distributes to both of them. You'll see below that where we have only 1 copper because the 2 That's the subscript behind the parentheses only pertains to the nitrogen and the oxygen. It distributes, so there's 2 nitrogen atoms and 6 oxygen atoms. So those are things that in here we just kind of assume that you know. So pay attention to that. It's got subscripts behind it, refer to the number of atoms. If you see a subscript outside the parentheses, it refers to everything in the parentheses. So that number will distribute. If the number is in front as a coefficient, then it distributes to the entire formula itself. So it's an important point that I wanted to point out. And I felt that because I hadn't talked yet, so I wanted to. Thank you.
And again, because these are substances, elements and compounds are 2 types of substances, it's going to have, these 3 are going to have the same formula, the same ratios of Bismarck, any other time, any other place, now into eternity. We're going to call salt by that ratio. And anywhere else on Earth, they would have that ratio too.
And I think at the fundamental level, if you had one single molecule of sugar, it's always going to have that ratio. If you're going to cut that single molecule of sugar and make it something smaller, it requires a chemical reaction. You must make something else. So in its fundamental unit, this is the ratio of each of those atoms. Okay? So compounds, if you're going to break a compound into something smaller, it requires a chemical reaction.
Now, the way that's drawn there in brackets and things, we're going to get to that. Those are called Lewis structures. You maybe have some experience with those already. But the way we look at, I guess this picture was for salt, we can draw it out showing 1 sodium and 1 chlorine in our structure. That's a ratio. That's our 1-to-1 ratio. In a sugar molecule, like in those cubes of sugar, there are little molecules, like Mr. Mitchell said. At the smallest level, that's how we would draw that molecule. And you're never going to have to draw anything that complicated, but we can. And that structure, if I'm an organic chemist or a nutritionist or something, I might be able to see that in a glimpse and know that it's sugar, just because I know what sugar looks like. That's its sign, that's its shape. And that ratio is the same all the time. That structure shows how those atoms go together. Copper nitrate, the same. There you can see copper and 2 nitrogens and 6 oxygens. And a picture of that blue, funky, like bright blue crystal. Stuff. So, as we go on to mixtures then, kind of just the opposite. Their composition can vary from place to place, from time to time, from moment to moment, from city to city, from beaker to beaker. And yet, we still call them by the same name. So mixtures are kind of I don't know how you describe it. They're a little trickier to pin down and talk about clearly, because the words we use to describe mixtures often can mean different things to different people. And so their makeup varies. We still call them the same thing. Sand, for example. And the Earth has sand everywhere. Continent, ecosystem, and climate. There's sand everywhere. And yet, that word, as you know, is a very generic one. The word sand might mean something very different to you if your only experience with sand is the stuff that's in a bag in the back of your pickup to get traction in the wintertime, or versus someone who lived their whole life in Hawaii and all they know is the Hawaiian beaches and what the sand looks like there. They're still calling that sand.
What color is sand? I mean, if you had to describe the color of sand, what would you say? Beige?
Or tan.
Tan?
Anybody been somewhere where the sand was a different color? White? Black?
I've been to a black sand beach. I've been to a green sand beach.
Yeah.
Yeah.
Where was that?
Right next to the Volcano National Park in Hawaii. So the sand was green. Why do you think the sand was green? Chloe, why do you think? Not algae. This was the actual sand particles themselves.
Good, that's what I was thinking was algae.
They were green. They were green. Very good. Why?
The rocks that broke down into the sand were green.
True. The rocks that broke down into the sand were green, probably made with some concentration of possibly copper or...
Could be a lot of stuff.
A lot of different elements on the periodic table have a green color to them. So the rocks that made up the sand that was broken down on that beach were green rocks or green sand.
You don't need to put all these formulas down, by the way, but when I did my master's, I did geosciences. I took a number of classes in geology in there. And was reminded then, you might take a geology class or geoscience and learn the same thing, that sand is really a description of the size of a particle. Well, sand is a particular sized grain. There's sand, there's silt, there's clay, there's pebbles and cobblestone, there's different sizes of pieces. Boulder has a very descriptive word meaning in geology. So sand is the size of a particle. It has really nothing to do with what's in it. This is just a few of the many different ways that we can write the formulas for sand. But their makeup varies from a tan to a whitish to a peppery, I don't know what you call that. And then up on the top left, a very, very black sand, a very white fossilized starfish, or what that is.
If we had to go back and play the game, Mr. Bleth and Mr. Mitchell, and the clue was as a sand collection from around the world, what would the answer be? Probably geology.
I do have a little bit of a sand collection, like collecting sand. It tells quite the story. That conversation today. So sand means all kinds of things. And depending on how close you look at it, I like the sand in the right side, but both of those are kind of the same, where there's lots of different colors in one handful. It's like a big blend of all kinds of cool minerals and stuff. So mixture, like salt water, that's a phrase we use, salt water. Salt water means a lot of different things. If I have a kettle of water on the stove and I'm going to boil some pasta in it, I might put a little salt in there. The flavor, that's salt water. If I'm going to gargle a sore throat, anybody gargled salt water for a sore throat before? Yeah. That's a lot saltier salt water probably than what you put in pasta. In other words, it tastes terrible when you get your noodles out later. So salt water can be a lot of different proportions. Maybe these are just some options, you don't need to get into the numbers in. But if I was going to make 100 grams of salt water, I might have 99.9 grams of water and just a teeny little pinch of salt. I might have 60 grams of water and 40 grams of salt. All of those could be called salt water, and yet they're all different. So that term, that mixture description of salt water is variable from one beaker or flask to the next. They would all look about the same. So if I say, which of those is salt water? Well, every single one of those is salt water. Unlike every single one of those is salt. NaCl, that's a very specific ratio. One sodium for one chlorine. Anything else, and it's not what we call sodium chloride. Kool-Aid, my brother. My brother's name is Sean. He teaches social studies, and he's a middle school principal up in the wonderful Phillips County in north central Montana. Malta High School, middle school. Sean's a wonderful guy. He's way smarter than me. I don't know if he didn't get there by drinking Kool-Aid, but one of the things he did as a kid was when he made Kool-Aid, he'd basically keep adding Kool-Aid to his glass, Kool-Aid, until you couldn't dissolve it anymore. Like there was like Kool-Aid at the bottom of the cup, silted at the bottom. So that was good. You drink it like that. You can hardly see through it. Well, if this was Kool-Aid like Sean's, his might be better than the one on the left. And it would taste like Kool-Aid intensely. So this might be the standard recipe for Kool-Aid, like, I don't know, the first one on the left. And if I start watering it down, it's still going to contain the same stuff, but in a different composition. We see the same thing happening with lots of different solutions in the lab. Depending on the need, we might use a very weak or very strong concentration of, say, acid. If we put 12 molar hydrochloric acid into a reaction, we'll go nuts and react like crazy. If we use the concentration of hydrochloric that's in your stomach right now, it'd be much slower and much less intense. Your stomach couldn't handle the acid that we use in concentrated form, but it can handle the 0.1 concentration that's in your stomach right now. Same thing might happen with something as everyday as a drink. If you have a Mountain Dew and you put ice in there, and the water starts forming, melting from solid to liquid and watering down your drink. You go to lunch, you can get it in a cup holder in your car or your friend's car, and you come back after school and you grab it and you taste it, it's still kind of cold, and as it watered down. You wouldn't say that was Mountain Dew and nude, and now it's Sprite or tea or milk. It's still Mountain Dew, it's just really watered down. So it hasn't changed in terms of what's in it, but it definitely has changed in terms of the ratio of things. And that's what mixtures can kind of be. There's a term that comes in with mixtures that you're going to hear a lot in chemistry. That word is aqueous or aqueous solution. It's probably something that you naturally would get. But aqueous, kind of hidden within there, is that word aqua that we know has to do with water. So aqua, like an aquarium, versus terrarium, water versus earth, right? So aqueous is like aquarium, water-based solution. Aqueous meaning something's been dissolved into water. And so when you're making a solution, you're talking about mixtures. This is commonly the way we'll do. We don't always dissolve stuff in water, but it's the easiest thing to use, it's cheap, it's safe, and it dissolves nearly everything we need. So aqueous solutions, when you hear that word, feel free to use that word. We abbreviate aqueous solutions, we put them into a lot of chemical reactions. This could be any, the dissolved stuff could be a solid, like sugar, or salt, or some mineral in the ocean. The dissolved stuff could be a liquid, like alcohols, or a syrup that you dissolve. Dissolved stuff could be gases, like carbon dioxide. If you ever had a soda stream or you carbonated a drink, you know that carbonation is there's grades of that. Faintly carbonated soda like Mountain Dew versus very fizzy things like Diet Coke. So again, aqueous solutions of gases work just the same. And when you see it, it'll be usually abbreviated like that. That might be something you haven't used as much or in a while, and when you see a little AQ in parentheses, that's referring to that thing dissolved in water. So to show you salt water, you'd see NaCl, a little AQ by it. That would tell us the state. That would tell us that salt that dissolved in the water. And now I better care about how much salt has been dissolved into how much water.
And if it were just a solid, I don't know if this is on your slide, just sodium chloride itself, would have a little S in parentheses next to it, meaning it would be a compound of that. As soon as you see the AQ, meaning it's dissolved in water, then it would become a mixture.
Same salt, different form. Physical change, right? Dissolving something is just a physical change. The same salt, different form. You just get in, you've been coming in late, we said at the beginning, this stuff's all posted up in the classroom, you can add this into your notes too, so if you need to play catch up, I would definitely try to jump in where we are and start adding that stuff to your notes from there. A good example of a mixture we often forget about is just the air you breathe. It's the pie chart that more or less breaks down typical air. Air is a mixture. Whether we call it a solution or not is kind of one of those things that's a conversation that's really not that terribly important. But it's a mixture, and it can vary from place to place. Boy, we know. If you pull up the Legacy on the wrong morning and park it by the gym, and the breeze is coming in from the east, and there's a smell off the lagoon by the KOA, God, that air is different than it is on the day when the wind's blowing out the west, and there's fresh air coming from the rest of it. Well, that's Bismarck, which by comparison isn't much fresher. It's all air, but boy, does it stink on the day when the wind's coming from the wrong direction. So it can vary from place to place, and time to time, we still call it air. It's just a question of how long we want to be out in that kind of pollution before it starts soaking into our skin.
One year I was teaching in Columbus, Montana, and we had a CO2 sensor in the classroom, and we monitored the level of the CO2 throughout the day. It was amazing. I was shocked on how the concentration of CO2 increases throughout the course of the day when there's a bunch of kids in the classroom. Oxygen went way down, CO2 went way up. Just from the respiration of the kids in the classroom during the day, the concentrations changed quite substantially, I think. Like 4 to 5%, which is quite a bit.
Less oxygen by the time you're the last class in that room at 2:30 or versus first class at 8:10. It's going to affect your alertness a little bit, so just be blame it on the oxygen content in the room a little bit too. Smoggy air, volcanic pollution, ozone from a lightning strike. If you ever smelled ozone, you might have just thought of it as a sort of a passing smell of a thunderstorm. A lot of times you smell that. Another kind of mixture that we should talk to you about a little bit is an alloy. You've heard that word before. Alloy is a mixture. You see there's some coins, most of which look to be made of alloys. The only ones I really recognize there, I see a dime, and a bunch of coins from other places.
There's a penny.
Oh, there's a penny. And then you get some of these coins that are definitely alloys, like the penny, like the dime, where you can see there's just kind of one composition there. It's hard to know what's inside. We'll talk about that more later in the year, but you can definitely see there's a coin or two there where there's two different kinds of them, like on the right side there. That one's got a kind of silver colored ring around the coppery colored middle. That wouldn't be an alloy necessarily, but each of those two different zones could be an alloy. So an alloy is a mixture, typically including at least two metals and maybe more than that. Some alloys include 6, 8, 10 different metals. And there's lots of reasons for alloys. You should kind of be aware of the reasons why alloys are important. And they're kind of listed there. It could be that they're tougher, or they resist corrosion. They don't get as dirty, as cruddy looking as quickly. They're lighter. alloys that go into things like car design these days. There's a big conversation in the last several years about aluminum truck beds and Ford pickups, so whether that was worth the fuel trade-off or the lack of supposed toughness if you bang on it hard enough with your equipment and stuff. So there's trade-offs, of course, with alloys. Is it cheaper to make it that way? Does it look a little snazzier? Does the brass on a trumpet serve any particular purpose other than to protect it from corrosion and look really nice, to protect the sound? Maybe a nickel-plated one sounds different than a brass trumpet. People in music probably say that does have a difference. So there's lots of different stuff that comes into the use of alloys, but things like brass, things like bronze, things like steel, we wouldn't be able to sit in this room as effectively as we do without the alloys that we have. So there's steel. You don't need to worry about the particular statistics, but you can see it's got iron. A minimum, it says here, of 50%, a maximum of 99%. Carbon, chromium, manganese, and adding molybdenum. Stainless steel, there it says has some chromium blended. Lots of different alloys in our everyday life. Bronze, solder, if anybody does electronics work. Brass, certainly. A lot of variations in brass. We just did a lab in AP. We're analyzing brass samples. Something called mishmet that they apparently use in the flints of cigarette butts. I didn't know that until I saw it here a couple of years back. Which contains some really unusual metals, that are like some of the rare earth metals that aren't really easy to find. Cerium, lanthanum, neodymium, not your everyday kind of stuff you buy at Menards kind of metals, except I'm sure you can buy Michigan filters at Menards. So alloys, lots of those. Pretty much anything you look at in your everyday life that's made of metal is very like an alloy. Some of them aren't, but most everyday metals are mixtures of metals. If we jump past that, I don't think we need to worry about it. We hit the reasons why. Okay. Separation technique. So hopefully that first dot there, you've seen everything now. Mentioned at least a bit, and you've been able to add a little bit to your descriptions there in those notes. The second file that was posted in Google Classroom was this one, separation techniques. So we're going to switch over to switch files really quick and have you open that one, if you haven't already done so. Open that Google Slides file that has separation techniques as the title, and we'll look at that one. This one's been started. It's been all set up for you, so it's kind of been in kind of a template for it. And now it's going to be up to you, once we kind of show you the first couple, to kind of finish it up. So this is all about separation techniques.
And this pertains to the salt and sand lab that we've been doing. You'll notice that there were a lot of different separation techniques that we used in that lab that you may have used without even realizing that this is a name for what you did. So a lot of this pertains to our separation lab that we had.
You say you had, I know you had salt, sand, and did you tell them what the other, they know the other one was?
Yeah, I called styrofoam.
So Mr. Mitchell's class had a salt, sand, styrofoam blend. Our class's blend is quite a bit different than that this year. So don't look for styrofoam if you get your sample board today in class. I am not getting this to project very nice. So hang tight for 1 second.
So as you look through that that file that we shared with you, you'll see that the format is very similar for each one of those slides. And the first couple slides were put together for you by Mr. Blatt. So within that, there's a summary of what the technique is. There's a picture that kind of shows the technique. And then there's a video link on centrifuging that you link on there to YouTube. So this is kind of the format we want you to follow and try to understand what centrifuging means. For those of you guys who've never seen the word centrifuge before, like when you go to get your blood drawn, a lot of times to separate the red and white blood cells from the actual plasma itself, they centrifuge it. Acceleration and force causes those larger blood cells to sink to the bottom and the plasma is left on top. So it's almost a form of pseudo-gravity, so to speak. You're creating centrifugal acceleration, which creates force, which is a lot like gravity pulling you to the earth, where the heavier particles within a solution then settle to essentially the bottom of the vessel.
Mr. Mitchell kind of gave you a sense. That's kind of what we want you to come up with. I guess we can watch the centrifuging video. Description there, you can use your own words, but make sure it's complete. Make sure it describes it well enough to where someone can understand just exactly what you're getting at. Doesn't mean, I'm not going to be too concerned about complete sentences, but you want to be thorough in your descriptions. And if you can find more than one picture that's helpful, great. If you can find more than one video, include those, that's great. There are lots of videos out. I went looking yesterday for one on, it was centrifuging. There were a lot of videos that showed it, but didn't necessarily show you much of what was going on. It's all kind of under the cover. I think the one that I linked there shows a little bit more completely, unless you see a little bit more of the detail. I also put in the same information for something that's a little more familiar and simple probably, which is simply condensation. The idea that condensation occurs when there's a state change, gas becomes a liquid. Something that you might not have known about condensation, that releases heat, or you have to remove heat, which is the same thing in terms of the heat transfer that goes on. It's the opposite of evaporation and boiling. And then I just kind of described here how we can use condensation to separate things at different points. And it gets into something we call fractional distillation. We actually use that over at the Mandan refinery where they separate oil out into several different components. And then a link down below underneath. So finding a picture that works to kind of help understand what it is in ways that maybe a description doesn't do on its own. And then a video, it could be any length. If you find a video that covers several different things, then certainly feel free to include that. Maybe just link there and then mention, start at a minute 20, and we'll kind of go over the look. I know I'm not going to go through and necessarily check every single video for every single person, but we're going to want to be able to go through everybody's file here, and open it, and just kind of flip randomly to one, and go look at the video and kind of see what you found. I don't know which ones it'll be. It will vary from person to person. But you want to work on getting that information included, description, video, and a picture. Each of those different techniques. So we've got crystallization, which may be rather familiar. Decanting, which you might have heard of before. And if you haven't, you're going to find out you probably have done just without calling it that. Distillation, evaporation, filtration. I noticed there we included a couple words, filtrate and residue. Make sure in your description that you mention what those two words have to do with filtration. Flocculation, and be careful about that, careful saying that one. Flocculation results in the formation of flock. And it helps you to remove things from mixture. In other words, it's an effective way to get the flock out. Gravity separation, reverse osmosis, and I think sedimentation is sitting. You get to those, you'll either recognize them immediately or like, I never use it.
Something I will be looking for is I want a summary. I do not want a copy and paste of the Google definition that you get when you type this word into Google. So if you want to lose points on this assignment for me, just copy and paste the Google definition and put it in there. Watch the video, learn what it is, summarize it in your own words. Okay, so that's part of this assignment. Those of you in my class tomorrow, we are going to work on this class some. So don't feel big rush to get it done.